Assalamu alaikum. Welcome back to BIOS course. Today we are going to see lecture 9, which is about analysis of continuous data. In previous lecture, we have seen the analysis or the test used for analyzing categorical data. Today we are going to see what the analysis of continuous data. Namely, we are going to see t-test and one-way ANOVA test. Okay, two well-known statistical tests, t-test and one-way ANOVA test. Okay, the learning objectives of this lecture are: number one, understand the concept of dependent and independent samples. Okay, dependent and independent samples. Two, describe the properties of student t-distribution. Student t-distribution is t-test. It is a well-known statistical test and very important one. Number three, conduct a formal hypothesis test of a claim about two population means using dependent and independent t-test, but with using the software StatDisk or JUMP. That means you are not going to manually calculate the statistics of t-test. Okay, instead of that, we are going to use JUMP, for example, or StatDisk to generate the results of t-test. Number four, conduct a hypothesis test of quality of three or more population means using analysis of variance ANOVA, also using statistical software JUMP. Again, we have four learning objectives. Two of them theoretical and two are theoretical and practical. For theoretical concepts, you are need to differentiate between the concepts of dependent and independent samples and to describe the main properties of student t-distribution. For theoretical and practical objectives, we are going to conduct t-test and ANOVA test using statistical software plus understanding the main concepts, definitions, and characteristics of these two tests. Okay, look here. In this slide, we have three questions. Each of them describe different cases. Number one, is there a difference between male and female height? Is there a difference between male and female height? In these questions, we have two samples. Sample one, males, and sample two, females. We have two samples, males and females, and it is very clear that we have two totally independent samples. Okay, we have a sample of males totally independent, totally isolated, totally different from the sample of females, and this question is to examine if there is significant difference in height, okay, in height between male and female. So in the first question, we have a case of two independent samples. What about the second? Is there a significant reduction in the weight of diabetic patients after the dietary intervention? Okay, in this question, we are asking if there is significant difference in the weight of diabetic patients after the dietary intervention. It implies that we have two sets of data. Set one is weights of diabetic patients before, okay, before the dietary intervention, and the second set of data is the weights of diabetic patients after, okay, after dietary intervention. So we have two samples again. Sample one weights before and samples two weights after, but the two samples are related, okay, are associated, because the same patients or the same patients have observation before and observation after. So for each one of patients, we have two observations, we have two measures, one before and one after. So in this case, we have, yes, we have two samples, but these two samples are somehow related or associated to each other. So this is a case or an example of dependent samples. Okay, the third one is there statistical significant difference between the heights of the following groups of children: those who eat a healthy breakfast, those who eat junk food for breakfast, and those who do not eat breakfast. Okay, in this question, we have three groups. Group one, children who eat healthy breakfast. This is number one. Group two, those children who eat junk food, and group three, children who do not eat a breakfast at all. So we have three groups, we have three samples, but different from each other. Okay, these samples are different from each other. As sample one represents the group of children who eat healthy breakfast, which is totally different from the second group of children who eat junk food, and different from the third group who do not eat breakfast. Yeah, the three groups are different in one characteristic. This characteristics is breakfast. Okay, the nature of breakfast taken by the children. So regarding the nature of breakfast taken by the children, we can divide the children here into three groups: group one, group two, group three. Each group is different from the others. So again, case one represents two independent samples. In case one, we represent two independent samples. Case two show two dependent samples, and the difference between independent and dependent samples is that in the second dependent, the observations of two samples are somehow related to each other. Okay, in the third case, we have, yeah, more than two groups, and independent. Okay, independent and more than two groups. Okay, each case is treated using different statistical tests. For case one of two independent samples, we use t-test. Okay, t-test for independent samples. For the second case, we use also t-test for dependent samples. And for the third case of more than two independent samples, we use analysis of variance or ANOVA. So in general, t-test used for two samples, two means one independent and one dependent, and ANOVA used for more than two samples. Okay, let us start with inferences about two means independent samples. Okay, two independent samples, the first case. And before that, look to the definition of independent and dependent. Okay, for independent samples, the two sample values selected from one population are not related to or somehow paired with the sample values selected from other population. We have totally different population, population 1 and population 2. From the first one, we select the sample values, and from the other population selected different sample values, and these sample values are not related or somehow paired with the other one. For the dependent, as you know, if the values in one sample are related to the values in the other samples, the samples are dependent. Okay, related to other sample, or sometimes called matched pairs, the same, or paired samples. All are the same: dependent, matched pairs, or paired samples. Okay, here I have comment. Okay, of a small comment here. For samples or for data collected from husbands and wives. Okay, husbands and wife. Yeah, yes, it's totally different. We have a sample of husbands and wives, but statisticians consider samples taken from husbands and wife to be dependent. Okay, this is a small note. Okay, uh, here we have examples of difference between independent and dependent samples. See the first one: testing the effectiveness of new drug given to group of patients, okay, while others while other group of patients given placebo, okay, given placebo. So here we have two groups: group 1 patients who given the new drug, and group 2 is the patients who given placebo. Group 1 given drugs, group 2 given placebo. So we have totally different groups. So here we have independent samples. Okay, the second one, testing the effectiveness of new drug by measuring blood pressure in patients before and also measuring blood pressure after, okay, having the drug. Any example or any case of patients before and after, okay, or taking data from patients or from any cases before and after, this is an example of dependent or matched pairs variables. Okay, we have data taken from the same cases before and after. Number 3, the accuracy of verbal responses in testing is tested in an experiment in which subjects report their weights and they are then weighted on a physician scale. The data consists of reported weight and measured weight for each subject. So for each one we have two observation, we have two measures. Okay, measure used measure 1 using reported, okay, or subjective one, and measure 2 or observation 2 is the measured one using physician scale. So we have dependent, okay, we have dependent samples. Next, the effect of sugar on the net weight of the contents of can of cola is tested with a sample of cans of regular Coke and other sample of cans of diet cola. So we have two different: regular Coke and diet Coke. So we have independent samples. The last one, in a research on the factors related to diabetes in children, research examined the factor used using a sample of 200 children, 100 patients and 100 free DCs. Okay, 100 of them patients are different, 100 is free of disease. So we have independent samples. Okay, now, as I said before, for dependent and independent two samples, we use t-test. Or student t-test, the same. This test, which is commonly used in statistics, is invented by Ghost as a more precise method for comparing two groups. Is the most commonly used method to evaluate the difference in means between two groups. Okay, note that. Okay, it's very important to note this student t-test is used for two groups. Okay, the groups can be independent, like blood pressure of patients who were given drug versus control group who received placebo, or dependent, like blood pressure of patients before versus after they received drug. So t-test can be used for two cases, okay, or for both cases, independent and dependent two groups. Also can be used even if the sample sizes are very small, as long as the variables are approximately normally distributed and the variation in the two groups is not reliably different. Okay, the t-test can be used for small groups as well for big samples. Okay, here we have the statistical assumptions for using t-test for independent samples. Okay, let us start with independent samples. Number 1, simple random samples should be taken in a simple random way. Number 2, normality. The parents population from which the sample is drawn is normal. If the distribution is seriously skewed, the t-test may be inappropriate. Okay, t-test is somehow flexible to normality, but if the distribution is seriously skewed, the result will be invalid. So we need approximately normality of the population, okay, from where we take samples. Number 3, we have independence. The sample observations are independent. Here, the independence means that the observations, okay, in each sample should be different from each other, okay. Observations inside each sample should be independent. Number 4, homogeneity of variance. This is important also. It means that variances of two groups studied are similar, okay, because when the variances or the variation in one group is highly greater than variation in the other group, the results will be invalid also. Anyhow, we have 4 assumptions for using t-test in independent samples. Number 1, simple random samples. Number 2, normality of population from where we take as a samples, independence, and homogeneity of variance. This is important. Okay, hypothesis test using t-test for independent two samples or for independent means. This is a test statistic. T is the test statistics equal x bar 1 minus x bar 2 minus mu1 minus mu2 divided by square root of s1 square over n1 plus s2 square over n2. You know, T here represents the test statistics of t-test for independent samples. X bar 1, you know, it is the mean, okay, mean of sample 1. X bar 2 is the mean of sample 2. Mu1 is the mean of the first population, and mu2 is the mean of the second population. S1 square is the standard, is the variance, okay, this is a variance of sample 1, and S2 square is the variance of sample 2, and 1 and 2 are sample 1 and 2 sizes. Anyhow, this is the formula used to calculate the test statistics in two independent samples. But as mentioned in the learning objective of this lecture, we are not going to manually calculate the test statistic. Okay, we will use software to generate the results. For example, this is an example taken from the American football baseball. Here we compare, or we want to examine the difference between two players, I think, Maguire and Barry Bonds, okay, in American football. Anyhow, we have two samples, two independent samples of runs, of hits, of run hits, yes, run hits records. Number 1 for Maguire, number 2 for Bonds. For Maguire, sample size N1 is 70, and for Bonds is 73. X bar, the mean of the sample 1 is 418.5, and the second is 403.7. S is the standard deviation of the first set is 45.5, and S, the standard deviation of the second set, is 30.6. Okay. Use 0.05 significance level to test the claim that the distances come from population with different means. Okay, here the word different is important in stating the alternative hypothesis. Anyhow, H naught, the null hypothesis, mu1 equal mu2. This is constant. Okay, in two independent samples, mu1 equal mu2 means that no significant difference between two means. H1, the alternative hypothesis, as you know, depends, okay, on the researcher's claim. Here the claim is examining different means. So mu1 doesn't equal mu2 as in the original claim. Okay, using software, using statistical software to generate the results, and look here. These are the results. It is very important to identify the test statistics, which is 2.27. This is the test statistics, and the most important result is the p-value. You know, we have two approaches, okay, in making decision on the null hypothesis. Either to compare, okay, the test statistics computed by the critical value, or to directly see the p-value and compare the p-value with the alpha, which is 0.05. Now, let us take the p-value of the test. The p-value of the test is computed to be 0.0248, okay, from statistical software. comparing 0.0248 with the significance level, which is 0.05. And you know, if the p-value, okay, if the p-value is less than 0.05, the decision is to reject the null hypothesis. Again, p-value is less than 0.05, so we reject H naught, and concludes that the mean difference or the mean distances are different. Again, the p-value is significant. Significant means it is less than 0.05. So the decision is rejection of the null hypothesis and concluding that the mean distances are different. Okay, you should know t-test for independent samples. You need to know the null hypothesis, the alternative hypothesis. You also need to know the value of test statistics from the output of software and the p-value. Make decision on H naught based on p-value and draw your conclusion on results. Here is an example in JUMP statistical software using independent samples. The file is called diabetes, okay, and we are going to test whether blood pressure differ by gender. Okay, that means male sample, female samples. We have a set of data of blood pressure for male and for female, and we are going to examine if there is significant difference. Okay, you know, H naught mu1 equal mu2 constant. H1 depends on the claim, and it claims that differ, okay, if there is difference in blood pressure. So mu1 doesn't equal mu2. In the results or in the output, it showed that first, if there is significant difference in the variances, as you know, one of the assumptions is homogeneity of variances. Okay, there is a test called leave-in test. This leave-in test examines if there is significant difference in variation or in variances between two samples. Okay, this is leave-in test, and this is the p-value of the test. The p-value is 0.399, no significant difference. So the p-value of the leave-in test is greater than 0.05, indicating no significant difference in variation. So if the p-value is less than 0.05, this is an indication of significant difference in variation, which against the assumption of homogeneity of variance. Now we check homogeneity of variance. Next, we run the test, and this is the test statistics. This is the value of t is 5.209. Don't care much about the value of the test statistics, but the important value is the p-value. Here is 0 is less than 0.0001. So the p-value of two-tail test shows significant difference in blood pressure between male and female. Okay, showed significant difference between male and female. Okay, because the p-value is less than 0.05. Now let us move to the second case, which is the t-test used for inferences from matched pairs or dependent samples. Okay, for dependent samples. Here we have assumptions. We have three assumptions. Assumption one, as in independent samples, the sample should be taken in simple random way. Number two, also we need normality. Okay, normality. The differences for the matched pairs are normally distributed. The differences between the matched pairs should be normally distributed. Number three, dependence. The sample observation are dependent or matched paired. Okay, and this is the first point. Okay, for using the paired samples t-test. Okay, again, simple random samples, normality, and dependence. These are the statistical assumptions for using paired sample t-test. Okay, this is the formula used to compute the test statistics. T is the test statistics for dependent samples. D bar is mean value of the difference D, okay, for the paired samples. So first computer will compute the difference, which is observation 1 minus observation 2 for each case. Then the D bar, which is the mean of the differences, and standard deviation of the standard deviation of the difference is d. Anyhow, as in independent samples, we are not going to manually compute this. Look here. This is an example of using captopril drug to lower systolic blood pressure. Okay, we use this drug in a sample of patients. This is the blood pressure before using the drug, and this is the blood pressure after using the drug, and it is claimed that this drug lower systolic blood pressure. So we are testing whether systolic blood pressure differ before and after treatment. Okay, so we are going to examine if blood pressure differ. Anyhow, this is H naught mu D equals 0. That means the mean of differences is 0. It means that no significant difference, and H1 mu of D doesn't equal. Okay, as said, differ in original claim. Okay, here, look here. This is the mean, for example, after using the drug, and this is the mean before using this drug. This is the mean of blood pressure. It was 185, and after using the drug, the value is 166. This is the test statistics. Yeah, still there is significant, or there is a difference. Okay, but the p-value of the test will tell us if the difference is significant or not. Anyhow, the p-value is significant. It is less than 0.05. Therefore, we reject the null hypothesis. We conclude that there is sufficient evidence to support the claim that the mean measure of systolic blood pressure before and after treatment are different. Okay, are different. It can also be concluded that the treatment is effective because the mean decreased after use the drug. Now, let us move to the third case, okay, which is the case of having more than 2 independent samples. And as I said before, in this case, we are not going to use t-test. Instead, we are going to use analysis of variance ANOVA. This statistical method or approach used when having more than 2 independent samples. Okay, so what is ANOVA? ANOVA is a method of ascribing variation in data to separate sources. This is a definition of ANOVA. It is a statistical method used to ascribing variation in data to separate sources. For example, the variation in observation can be attributed partly to the way observation vary from one to another within a group, or partly to the way the group means vary from one to others. Okay, so in general, we have two types or two parts of variation. The first is within the group, and the second is between the group. Okay, the methods of ANOVA or analysis of variance try to isolate within from between group variations. The idea is like this. Let's say we have three group of students. Okay, group 1, let's say students of College of Medicine. Group 2 is students of college, let's say, of dentistry, and group 3 is a college of applied medical sciences. Okay, the difference, and we are going to see if there is significant difference between the performance of the three groups in certain course. Okay, the difference, the general or the overall variation between students, the overall variation of between students can be partly because of variation inside or within each group, or also can be due to variation between the three groups. Okay, any variation between more than two groups can be partly because of variation inside the group, or the variation between groups. Anyhow, ANOVA method is a method used to ascribe variation in data to separate sources, to isolate this variation into two sources. Source 1, the variation inside or within groups, and the other one, the variation between groups. If the variation between groups, okay, is greater than variation within group, so we can say there is significant difference. Okay, there is significant difference between groups. This is a general idea. The method used is called one way. It's called one way because we are going to examine one characteristic, okay, like performance of students, like height of students between groups. So in each case, we are interested in only one characteristics. Yes, there is another method called second way or two-way analysis of variance and so on. We assume that observations are mutually independent. Inside each group, we have independent observations, normally distributed, and have constant variance. These are assumptions, okay? Independent, normal distributed, and constant variance. Now, we test the hypothesis that three or more population means are equal. You know, if you have only two independent samples, we use t-test. So the null hypothesis is that mu1 equal mu2 equal mu3 up to mu k, okay, where k is the number of groups. The alternative hypothesis h1, not all mu I are equal, or precisely we can say that at least one of the groups means differ from the rest. This is a better one. At least one of the group means differ from the rest, or shortly, at least one mu I is different. Okay, you know, if the b value is less than 0.05, that means if b value is significant, then we have to do something called post hoc test. Okay, if we have significant difference, we use post hoc test to determine which group differ from the rest. There are many post hoc talks like Tukai, like Pomfroni. Anyhow, will be done using the software. Here we have analysis of variance summary table. You need to know only that source of variation we have among or within. We have between groups and within groups. For each, we have sum of squares, mean of squares. Anyhow, the final is the value of the test statistics called F. So what is F? F is the test statistics of ANOVA. Okay, F is the test statistics of ANOVA. ANOVA used F distribution. The procedure H0, mu1 equal mu2 equal mu3 up to mu k. Use GAMP to obtain the results. This is the statistical software. Identify the b value from the display form a conclusion based on this criteria. You know, if the b value is less than 0.05 or alpha, reject the null hypothesis of equal means. Otherwise, if the b value is greater than alpha, fail to reject the null hypothesis of equal means. For example, we are going to use GAMP to test whether the cholesterol level of June, okay, differ by treatment. We have four different treatments. The objective is to test whether cholesterol level is different by treatments. As we have four treatments, so the null hypothesis mu1 equal mu2 equal mu3 equal mu4, that means no significant difference. H1, the mean cholesterol of at least one treatment is different from the rest. Okay, this is a way, or this is a stating of the alternative hypothesis. Next, the GAMP outcomes. Okay, this is a GAMP outcome. This is the analysis of variance table. And as I said before, this is the F ratio or the test statistics or F statistics. And here is the B value. Okay, the most important is to identify the b value. The b value is less than 0.0001. It is highly significant. So b value is significant because it is less than 0.05. We conclude that mean cholesterol of at least one treatment differ from the rest. Okay, so we reject the null hypothesis, and we have sufficient evidence to support that at least one mu is different. Therefore, we need to perform post hoc test. Okay, If p-value is significant, we need to identify which group or groups is different. That means going further, performing post hoc test. Here is the post hoc test. Okay, it is like t-test for each of two independent samples. It's something like running t-test. For example, the four groups, let us say our first, the four groups are treatment A, treatment B, control group, and group given placebo. So we have four treatments: treatment A, B, control means nothing, and given placebo. Look here, control versus A, control versus A. The p value is less than 0.05. That means control is significantly different from group given A drug. What about placebo versus A? Also, it is less than 0.05 difference. Control B difference. Placebo versus B difference. Drug B versus drug A. Also, it is difference. There is difference. But what about the last combination, which is control versus placebo? The p value is greater than 0.05. It means that there is no significant difference between control group and placebo group. So control and placebo looks or gives the same outcome. So the different groups are A and B. Again for each combination, for each significantly different combination, we have either A or B. So A and B are differ significantly from the others. Again, control and placebo looks the same, so the different groups are A and B. Here we have also further example of using stat disk in two independent samples, and this is a b value. This is a b value as computed before, which is less than 0.05 and rejecting the null hypothesis. Thank you for attention, and I will upload more exercises on t-test and ANOVA. Assalamu alaikum.